Professor Lukin, you present your work in this conference. This is one thing. If you meet somebody at a party, somebody who does not know you and is not an academic, what do you tell them? What is your work?
So my laboratory pursues two big goals. One is we are trying to figure out how to build quantum machines, in particular quantum machines which are in some sense large. That means a large number of qubits, or quantum machines which are spread, such as quantum networks around, by kilometers, maybe eventually hundreds of kilometers. And one of the outstanding questions in our field is to figure out if these truly large-scale quantum machines, that's quantum computers containing millions of qubits, if they can be built and how. But the second question that my lab is trying to answer is how to make these machines useful. And that is, we are trying to understand what kind of algorithms and applications these machines can do that classical machines cannot do. So these are the two goals of my laboratory.
And is this a theoretical approach, or are you doing this with experiments?
So my group is unique because it combines both theorists and experimentalists. And moreover, we are now also, when we're trying to look into real-world applications, we also collaborate with industry. And I'm a co-founder of two startup companies, Quera Computing and Quantum Diamond Technologies.
I read that the IBM machine Osprey combines 433 qubits. And as far as I know, this is the largest or the biggest quantum computer. And you are talking now about millions and more. There is a big gap between what is possible today and what you are aiming to.
So we believe that our laboratory is at the cutting edge of actually building largest quantum systems. In fact, in my talk tomorrow, I will present some early, experiments showing that we can actually now start to experiment with about 1,000 of quantum bits. There is still the big gap, of course, to millions, but we are now entering kind of a very special point in time where we can build machines and experiment with machines which are large enough, programmable enough, and coherent enough, such that we can really do the things which classical computers cannot do. And it's a very special moment in time. And we hope with these new developments, we can A, learn how to scale up machines to millions of qubits eventually. And B, we also hope we can really start addressing this application challenge. That is, really learn what these machines can be good for. And, already in our lab, for example, we have done experiments where we made discoveries, scientific discoveries related to scientific applications. So I would say on that front, we already are moving to the point where, the machines become useful scientific tools. But we also, of course, are hoping to extend the domain of applications to make an impact on real-world problems, address real-world challenges, and things which are of interest beyond just the community of quantum scientists.
That's a good point. Until now, quantum computers mainly are built to resolve just one special problem, and then they are very good. They are really performing. And do you think you will be able to transfer the application of quantum computer from special problem solving to a general calculating machine?
Well, let me just, certainly it's my hope that this will be the case. But let me just, step back, when we talk about scientific applications of quantum computing, we're not talking about just one specific problem, but we are talking about a class of problems which are fundamentally quantum mechanical. And so basically with machines like the ones which are in our lab. And by the way, in our lab, we already have been operating 256 qubit machine for already more than 2 years, for almost 3 years. And we use this machine to really make scientific discovery. What I mean is really create states of matter which have never been created. Mm-hmm. And, address problems which have been, like challenging to solve with any conventional methods for nearly 5 decades, So this is what I call, so it's not just one specific problem. It's a class of the problems, admittedly the problems in quantum physics, which these machines already help to address, to solve, And what we are hoping is to extend these problems, to much broader domain, domain which touches on chemistry, biochemistry, domains which touch on things like optimization, logistics. And in fact, I will be reporting tomorrow some results, showing how the solution of these so-called optimization problems, the problems which, for example, like in logistics, are, very important, how the solution of these problems can be accelerated using quantum computers. But of course, these are still in the early stages. We're just still experimenting with relatively small scale problems. But, we start seeing examples where quantum computers can really help solve real problems faster and better than using the conventional machines.
I hear in many interviews that I have now at this conference the word hope. And there is a lot of hope in all the work, a lot of enthusiasm, of course, but a lot of hope. And I compare to a completely different physical problem. This is the nuclear fusion. Yeah. Since years, decades, they are having hope and they're building big machines and they are far away from a commercial application of nuclear fusion because perhaps the problem is too big. Could it be that the quantum computer is too small? But I'm talking about, or we are talking about scales of one atom, one electron. Could this be perhaps too small?
So you're asking whether fundamentally quantum computers might be just too difficult to build.
Yeah, I mean, the theory is okay. Like in nuclear fusion, theory is okay, but they cannot build it.
Yeah, so...
Or if for some milliseconds. And
it's a very good question. And, of course, we need to do these things before we can answer. It's very difficult to predict the future. But I would maybe like to point out that, in some ways, for example, in the domain of like scientific applications, I would say we already crossed the threshold where we're not talking about the hope, but we're talking about reality, right? We're talking about, scientific discoveries made which really affected now, like the way how people think about certain things, And, if you'd like, I can give an example of one of them. But, there are not so many examples yet, but, I hope there will be more. But certainly there are, these machines which we already have now, they become a very useful scientific instruments. And to me, it's a little bit, I think the quantum computers now is where classical computers were in maybe 1950s. So at the time, people built some computers, and, scientists started using them to do scientific simulations. And, some of the simulations were very important for things like nuclear energy and so on, early on already. But, certainly we could not have predicted that each of us will carry the computer in our pocket.
And it was even worse. IBM thought there will be a need of a few dozen computers worldwide.
Yeah, and that is why, right? Because it was clearly useful scientific tool already at the time. But people could not imagine, what you could all do with that. So to me, it feels like in many fields, like quantum is now, people say that, often people kind of overestimate the promise in a short term, but underestimate the promise in the long term. And I think it certainly applies to that, And what is special about the time? And the second thing why I say is I'm not actually talking about the hope, anymore, because we are now, building machines which are large enough, programmable enough, and quantum enough that we can really start exploring what these machines can do. And I think this is very special time, because, and like some of the calculations we can do, maybe they are not necessarily outperform the existing, best possible computers, but we already can predict, along which axis we'll have most promising applications. And this is, I would say, even before we deployed some of the most amazing tools which we know we should be able to deploy. And, here I mean some, examples like quantum error correction. I mean, it's a little bit technical term, but, that's a next big frontier, which several talks will address here. So the problem is, the reason why quantum computers are difficult to build is because big objects tend to become classical. And the reason is that fundamentally, if you do quantum computation, if you do quantum operations, you make errors. And these errors basically make the system which is fundamentally quantum behave like classical. That's the reason why everything around us is classical. And I think we are now at the point where we will be able to start deploying techniques. And this is an amazing theoretical development in the field, which happened 20 years ago, that people pointed out that you can use fundamental quantum properties, in particular something like entanglement, to correct the errors in quantum computation. And I believe we are now at the point where we can really start deploying this technique, and this would make it, even more special time. So we have now big enough systems, enough control, and enough programmability to really start utilizing.
So you feel like being at the starting point of a new development.
Yes, it is absolutely. It's a very special time in our field.
Okay, let's talk. You mentioned the word. Let's talk about little to conclude the talk. Let's talk about the physics or the quantum physics. We learned that there are mainly two mechanisms or maybe two phenomenons. This is the superposition, and I've learned there is a comparison, a coin that spins. On one side is a one, on the other side is the head, and head and one can be at the same time as long as it spins. But entanglement, give me a good example or explanation of entanglement.
Yes, in a way it's very simple.
Oh, that's nice. In a way it's very simple.
So,
okay.
And basically superposition and entanglement is what gives quantum machines their power. The power that classical
Concentrate
machines.
on entanglement.
I'll explain them both. So,
okay.
So the idea of superposition is a notion in quantum mechanics that some objects can be in several different states at once. They can be, here and there. And, that does sound a bit bizarre, but like through the experiments carried out over more than a century, we have been repeatedly witnessing, almost by now daily, that at a microscopic world, this is possible, And the entanglement is a special type of superposition where basically this object is in different places, kind of non-locally. So it can be here and there at the same time, like this chair can be here in Basel, or can be in Boston, or can be in Chicago. And it's in principle possible.
Everybody would say, no, that is not possible.
It is not possible, and of course it does not happen in a macroscopic world. Okay. So these superpositions and entanglement is what gives quantum machines, quantum computers, quantum sensors, quantum networks their power. So basically what you do to build a quantum computer, you prepare superposition of different states of quantum bits you just prepare many combinations of them. And what quantum computer does, it basically processes them all at once. And what's staggering is that, for example, if you take a system of, say 300 qubits, I will talk about this tomorrow, with 300 qubits, you can encode and process more information than the number of particles in the universe. That's what gives these quantum computers their power. And during that operation, during the processing, this superposition means that different qubits are kind of flip differently. It constitutes what's called entangled state. And, one remarkable property of this entanglement, you can also take things and move them apart, right? For example, you can separate by your parts of your entangled systems by tens of kilometers, And this is what gives quantum networks their power. So all of these are very counterintuitive, seemingly very bizarre kind of concepts and ideas, but the important thing is that they were confirmed in experiments over last century, and we are now starting to deploy these ideas and concepts to real-world, practical, useful applications.
I'm not sure whether I really understood entanglement, but I like very much your enthusiasm. I thank you very much for that talk.
Thank you. Yeah.